On the 14th of November, 2023, a machine that had been talking to Earth for 46 years without a serious interruption suddenly stopped making sense. It did not go quiet. That is the part worth sitting with for a moment, because a quiet spacecraft is the easy failure to understand. A transmitter burns out, a battery dies, an antenna drifts off target, and the signal falls below what any receiver on the ground can pull out of the static. None of that happened. The signal from Voyager 1 kept arriving at the Deep Space Network right on schedule, at the correct frequency, at the expected strength, from exactly the direction in the sky where the spacecraft was supposed to be. It was pointed correctly. It was receiving commands from the ground and acknowledging every one of them, by almost every measure an engineer would use to check whether a spacecraft is alive. Voyager 1 was alive. What it was saying, though, made no sense at all. Instead of the carefully packaged stream of science and engineering data that had been arriving for decades, the Deep Space Network was picking up a repeating loop, over and over, carrying no usable information whatsoever. The spacecraft had a voice. It had simply forgotten how to use it. This alone is a strange kind of failure, and it is worth explaining why before going any further, because the strangeness is the whole story. Voyager 1 is, right now, the most distant object ever built by human hands. It is roughly 24 billion kilometers from Earth, a distance so large that a radio signal traveling at the speed of light needs about 22.5 hours just to make the one-way trip. A command sent from the ground takes nearly a full day to arrive, and the spacecraft's response takes another day to come back. Something breaks on a Monday morning, and you do not find out what it was until Wednesday. You cannot send a technician. You cannot power the thing down and restart it the way you would a frozen laptop. Every single decision about how to fix it has to be made from a control room in Pasadena, California, sent across a gap so large that light itself is a slow messenger, and evaluated only after nearly 2 full days of silence. That distance and that delay are going to matter again later in this story, because they explain almost everything about why fixing Voyager 1 is difficult and why, decades from now, this particular episode is likely to be remembered as one of the more remarkable repair jobs in the history of engineering. But first, it is worth understanding where this spacecraft actually is, and why the same instrument that stopped making sense in November of 2023 had, 6 years earlier, quietly recorded something that nobody on the team had expected to find at all. Voyager 1 left Earth in September of 1977, launched on a trajectory designed to take advantage of a rare alignment of the outer planets that would not repeat for another 175 years. Engineers at the Jet Propulsion Laboratory called it the Grand Tour opportunity, a chance to sling a single spacecraft past Jupiter, Saturn, and potentially beyond, using each planet's gravity to bend and accelerate the probe's path toward the next target without spending a drop of extra fuel. Voyager 1's twin, Voyager 2, launched about 2 weeks earlier on a slower path that would eventually carry it past Uranus and Neptune as well. But Voyager 1 took the faster route, reaching Jupiter in March of 1979 and Saturn in November of 1980. Both spacecraft carried a suite of instruments designed to study planets, moons, rings, magnetic fields, and the charged particle environment of the outer solar system. Cameras, spectrometers, a magnetometer, a cosmic ray detector, a low-energy charged particle instrument, and a plasma wave subsystem built around 2 long antennas extending from the body of the spacecraft in a wide V shape. Nobody expected this hardware to still be operating in the 2020s. The primary mission was planned to last about 4 years, enough time to complete the flybys of Jupiter and Saturn. Everything after that was, in the truest sense, bonus material, made possible only because the spacecraft kept working and NASA kept funding the small team required to keep listening. After Saturn, Voyager 1's trajectory carried it up out of the plane in which the planets orbit, away from the ecliptic, on a path that would never again bring it close to another planetary body. There was nothing left to fly by. What remained was a long, slow climb outward, through the outer reaches of the solar system, through a region dominated by the sun's influence, and eventually into a boundary that nobody had ever directly sampled before. That boundary is called the heliopause, and it is worth being precise about what it actually is, because it is not a wall and it is not a sharp line you could draw on a map. The sun is constantly shedding material into space, a stream of charged particles called the solar wind, blowing outward in every direction at speeds that can exceed 1,000,000 kilometers per hour near the sun and gradually slow as it spreads thin across the solar system. That wind carves out a kind of bubble around our entire solar system, a region called the heliosphere, inside which the sun's particles and the sun's magnetic field dominate the local environment. Beyond the heliosphere lies the interstellar medium, the very thin material that fills the space between star systems across the galaxy, left over from earlier generations of stars and shaped by the collective winds and explosions of everything nearby. The heliopause is the boundary where those two regimes meet, the place where the outward pressure of the solar wind finally drops to match the inward pressure of the interstellar medium pressing back. On one side, you are still, in a meaningful physical sense, inside the sun's domain. On the other side, you are in the galaxy's domain. Voyager 1 crossed that boundary in August of 2012, based on a sharp change in the density and behavior of the charged particles its instruments were measuring, becoming the first human-made object confirmed to have left the heliosphere and entered true interstellar space. Voyager 2 would follow in November of 2018, along a different heading, giving scientists two independent measurements of where the boundary sat and how its shape varied. Being in interstellar space does not mean being in empty space. That is a common assumption, and it is wrong. The region between stars is filled with what astronomers call the interstellar medium, a thin haze of plasma, neutral gas, dust, and cosmic rays, so sparse that a single cubic centimeter of it might contain less than one particle. For comparison, a single cubic centimeter of the air in the room around you right now contains something on the order of tens of quintillions of molecules. The interstellar medium is closer to a true vacuum than anything that has ever been created in a laboratory on Earth. But it is not nothing, and one of the surviving instruments on Voyager 1 happens to be extremely good at listening to it. That instrument is the plasma wave subsystem, and the way it works is elegant in its simplicity. The two long antennas extending from the spacecraft do not broadcast anything. They listen. When charged particles in the surrounding plasma oscillate, they generate weak electric fields, and those fields induce tiny voltages in the antennas. Voltages the instrument can measure and convert into a kind of audio signal. Played back through a speaker, the result sounds like a faint static hiss, not unlike the sound of an old radio tuned between stations. It is, in a very real sense, the sound of interstellar space, translated into a frequency human ears can process. For the first several years after Voyager 1 crossed the heliopause, that instrument produced data mostly in short, dramatic bursts. Every so often, a shock wave triggered by an eruption on the sun, something like a coronal mass ejection, would travel outward through the solar system over the course of months, eventually slamming into the interstellar plasma far beyond the heliopause and setting it ringing, briefly but intensely. Particles in that outer plasma would oscillate strongly enough for the antennas to register a clear, loud signal lasting a few hours or a few days before fading back into what appeared to be silence. Between those events, the working assumption at the Jet Propulsion Laboratory and at Cornell University, where much of the plasma wave data was being analyzed, was that the ambient interstellar medium was simply too thin and too quiet to produce a measurable signal on its own. The shocks were treated as the only usable data. They were the only way to estimate the density of the plasma out there, the only way to take its temperature, in a manner of speaking, because there did not appear to be anything else worth measuring in between. Senior Cornell astronomer James Cordes offered a memorable way of describing what the team believed they were seeing. He compared it to a thunderstorm heard from a great distance. Each solar shock was a flash of lightning, loud, unmistakable, and brief, proof that something was happening out there, but telling you almost nothing about the conditions and the quiet stretches between flashes. For years, the assumption was that those quiet stretches really were quiet, that the absence of an obvious signal simply meant there was no signal to find. That assumption, that silence in an instrument, means the absence of a real phenomenon rather than a phenomenon too faint for the instrument's current sensitivity, is one that the history of physics keeps testing and keeps failing. It is worth walking through a few examples, because the pattern shows up again and again, and Voyager 1's story turns out to be one more entry in a very long list. Consider gravitational waves. Albert Einstein's general theory of relativity, published in 1915, predicted that massive accelerating objects, like two black holes spiraling into each other, should send ripples through space-time itself, stretching and squeezing distances by an almost unimaginably small amount as they pass. For 100 years, nobody had an instrument sensitive enough to detect that effect directly. It was not that gravitational waves were absent. It was that no detector on Earth could measure a distortion smaller than a fraction of the width of a proton until the Laser Interferometer Gravitational Wave Observatory, known as LIGO, finally achieved the necessary precision and detected its first signal in September of 2015. The merger of two black holes, more than 1 billion light-years away. The waves had been washing over Earth the entire time. Nobody had been listening carefully enough to hear them, or consider the neutrino. A subatomic particle so weakly interacting with ordinary matter that trillions of them pass through your body every second without leaving any trace. Neutrinos were first proposed on theoretical grounds in 1930 to explain an apparent violation of energy conservation in a type of radioactive decay, but it took until 1956 for an experiment to actually confirm their existence. Because building a detector sensitive enough to catch even a small fraction of these nearly invisible particles required entirely new techniques. Later, physicist Raymond Davis Jr. spent years running an experiment deep underground in South Dakota, mined specifically to catch neutrinos streaming from the sun, initially detecting fewer than theory predicted. A discrepancy that took decades and an entirely new understanding of how neutrinos behave to resolve. The particles were always there. The gap was in the instruments, and the theory needed to interpret what those instruments were seeing. The same story runs through the search for planets orbiting other stars. For most of the 20th century, exoplanets were purely theoretical, invisible to every telescope humanity had built. Not because they were rare, but because a planet's light is so overwhelmed by the glare of its parent star that direct imaging was essentially impossible with the technology of the time. The first confirmed detection of a planet orbiting a sun-like star came only in 1995, using a technique called radial velocity, measuring the tiny wobble a planet's gravity induces in its host star rather than looking for the planet's light directly. Once the technique existed, planets turned out to be everywhere. Thousands of them have now been confirmed. They were never scarce. The tool to notice them had simply not existed yet. Dark matter searches and the ongoing hunt for signs of intelligent life elsewhere in the galaxy follow the same logic today. In both cases, decades of null results do not prove the underlying phenomenon does not exist. They prove that the search has not yet reached the sensitivity or the specificity required to find it, assuming it is there at all. The history of astrophysics, looked at from a certain angle, is largely a history of lowering the detection floor, of building instruments and analysis techniques capable of noticing things that were always present but always too faint for whatever came before. For 5 years after Voyager 1 crossed the hill, nobody at Cornell or the Jet Propulsion Laboratory had gone looking for a signal in the quiet stretches between the solar shocks. Then, in the archived plasma wave data, a graduate student did. Stella Ocker was a graduate student in astronomy at Cornell University, working through the plasma wave archive that had accumulated since Voyager 1's crossing into interstellar space. She was not chasing a specific hypothesis. She was doing the unglamorous work of going through years of recordings line by line, paying attention to the sections that everyone else had treated as uninteresting. The solar shocks were the obvious story, loud and easy to point to. The quiet in-between was supposed to be nothing worth analyzing. It was in that supposed nothing that she found something. What she found was a signal at a single narrow frequency, extremely weak and remarkably steady, present in the data from 2017 onward. It did not flare the way the shock-driven emissions did. It did not pulse. It showed no correlation with any solar event that the team could identify. It was simply there, continuously, hour after hour, year after year, sitting beneath the threshold that anyone scanning for the dramatic signals had ever bothered to check. The finding was published in the journal Nature Astronomy on the 10th of May, 2021, with Ocker as lead author and James Cordes as senior author. Ocker later described the signal in a short phrase that captured its character precisely, very faint and monotone. It was, in effect, the persistent hum of the interstellar gas itself. Return for a moment to Cordes' thunderstorm analogy, because Ocker's discovery reframes it completely. The solar shocks were the lightning, dramatic and easy to notice, but revealing very little about the steady conditions between strikes. What Ocker had found was closer to a gentle, continuous rain, always falling, always present, simply too quiet for anyone to have separated it from the recording's baseline noise before. Cordes himself later used almost exactly that language, describing the interstellar medium as producing a persistent, gentle rain of plasma oscillation, punctuated occasionally by the sharper bursts triggered by activity on the sun. The scientific value of this discovery goes well beyond the pleasure of finding something unexpected. Before Ocker's work, the only reliable measurements of the interstellar plasma's density came from the rare moments when a solar shock arrived and set the medium, ringing loudly enough to measure, a method that provided, at best, occasional snapshots separated by months or years of blindness. With a persistent, always present signal identified, the plasma wave instrument could be used to sample the density of the interstellar medium continuously, tracking changes over distances on the order of 10 astronomical units, roughly 10 times the distance between Earth and the Sun, with individual readings fine enough to resolve structure across a few percent of an astronomical unit at a time. That level of resolution revealed something the earlier, shock-only measurements could never have shown. The interstellar medium is not smooth. It has texture, small-scale fluctuations, density gradients, and turbulent structure on scales that no instrument located anywhere near Earth has ever been close enough to resolve directly. The space between the stars, it turned out, has been quietly broadcasting information about its own fine-grained structure the entire time. Voyager 1 has been out there, in a register so faint that the only spacecraft ever positioned to hear it had been recording the signal for years before anyone thought to separate it from the noise floor and actually listen 6 years after Ocker first found that persistent hum buried in the archive. The very same instrument suite, on the very same spacecraft, would go from quietly revealing the texture of interstellar space to failing to make any sense at all, to understand what actually broke inside Voyager 1 in November of 2023, and why it took the team at the Jet Propulsion Laboratory 5 months to fix it. You need a basic picture of how the spacecraft's internal computers are organized, because the design is a product of a very different era of engineering. And that design is precisely what both saved the mission and made the failure so difficult to diagnose. Spacecraft of Voyager's generation, built in the 1970s, were designed with redundancy as a survival strategy, because there was no possibility of a repair crew and no possibility of a do-over. Voyager 1 carries 3 separate onboard computer systems, each responsible for a different function. One handles commands arriving from Earth, essentially the spacecraft's ears. Another manages the spacecraft's orientation and pointing, keeping its antenna aimed at Earth and its instruments aimed at whatever they are meant to observe. The third, called the flight data subsystem, does something neither of the other two can do. It collects everything the science instruments are measuring, along with everything the spacecraft's own internal sensors are reporting about its health, temperature, and power status, and assembles all of that information into a single, structured stream of data that gets handed off to the radio transmitter for the long trip home. The flight data subsystem is, in essence, the spacecraft's translator, the component that converts raw measurements into a coherent message. If the flight data subsystem breaks, everything else on the spacecraft can be functioning perfectly, and nobody on Earth would have any way of knowing it. That is exactly the situation the Voyager team found themselves facing. The symptoms all pointed toward a flight data subsystem failure, but confirming that diagnosis, let alone fixing it, required working through a communication delay of about 22.5 hours each direction, meaning roughly 45 hours from sending a single diagnostic command to receiving any kind of response. Send a command on a Monday morning, and you find out what happened on Wednesday. Guess wrong, and you spend 2 entire days discovering that you have made things worse rather than better. This is not simply a slow internet connection. It is a fundamentally different category of engineering problem, one that shows up in control theory whenever a system must be diagnosed and corrected without the ability to observe results in real time. Ordinarily, engineers troubleshooting a malfunctioning computer rely on a tight feedback loop. Try something, observe what happens, adjust, try again, often within seconds. At Voyager 1's distance, that loop stretches to nearly 2 days per cycle. Every single diagnostic step becomes a hypothesis that cannot be tested for the better part of 48 hours. And every command has to be conservative enough that even a wrong guess does not make the situation irreversible. It is closer to performing surgery through an intermediary who can only report back once every 2 days than it is to conventional computer repair. The team's approach was to send the spacecraft a request it effectively could not refuse to respond to in some form. A diagnostic command the engineers informally called a poke, instructing the flight data subsystem to interrupt whatever repeating process it appeared to be stuck in, and instead dump the complete contents of its own memory back to Earth. Every byte of code, every variable, everything currently stored in its circuits. The idea was simple in concept. If the team could see exactly what the flight data subsystem currently held in memory, they could compare it against the original specifications documented back when the spacecraft was built, and identify precisely where the two diverged. That poke command was transmitted on the 1st of March, 2024. For 2 days, nothing useful came back, only the same repeating pattern the spacecraft had been sending since November. Then, on the 3rd of March, a section of the returned data stream looked different from the rest. Not immediately readable, but structurally distinct from the surrounding gibberish. Somewhere inside the malfunctioning stream, the flight data subsystem had actually done what it was asked. It took the engineering team about a week of careful analysis to decode what they were looking at. By the 10th of March, they had confirmed it. The unusual section was a memory dump, exactly as requested, containing the full contents of the flight data subsystem's internal storage, transmitted line by line across billions of kilometers to a control room in Pasadena, California, with the dump in hand. The Voyager engineers laid it side by side with the original design specifications, decades-old documents describing exactly what every section of the flight data subsystem's memory was supposed to contain, and went through it piece by piece, looking for discrepancies. What they found was that roughly 3% of the memory did not match what it should have contained. 3% sounds small, and in absolute terms, it was small. The flight data subsystem carries a total of about 68 kilobytes of memory, an amount smaller than a single photograph taken on an ordinary modern phone. But every one of those bytes had a specific job to do, and losing even a few kilobytes worth of function inside a system with essentially zero spare capacity was enough to break the entire chain that packaged data for transmission. Crucially, the errors were not scattered randomly across the memory. They were tightly clustered, concentrated in a single region, exactly the pattern you would expect if one specific hardware component responsible for storing that region had simply stopped functioning. A single chip inside a machine nobody had physically touched in 46 years had failed. Why it failed is something the team at the Jet Propulsion Laboratory has been careful never to claim certainty about, because there was no way to physically examine the failed hardware, and likely never will be. 2 explanations were considered plausible, and both remain on the table. The first is that a high-energy particle, a cosmic ray, struck the chip at some point and damaged it directly. An event engineers call a single event upset, a well-documented and catalogued failure mode in electronics, particularly outside the protective bubble of Earth's magnetic field. The interstellar medium Voyager 1 now travels through is bathed in energetic particles moving at relativistic speeds, and even a single well-placed strike on the right transistor can flip a stored bit permanently or damage a circuit junction beyond recovery. Modern spacecraft electronics are specifically radiation hardened to resist exactly this kind of damage, using techniques that either did not exist or were not yet standard practice when Voyager 1's hardware was designed in the early 1970s. The spacecraft's electronics predates that entire engineering discipline by roughly a decade, and Voyager 1 was never designed with the expectation that it would spend years operating far beyond the heliopause, deep inside a radiation environment. Its original engineers had no way to fully anticipate. The second explanation is simpler and no less plausible. The chip was 46 years old, and it had been operating continuously at extremely low temperatures, under conditions its original designers never tested for longer than the careers of most of the engineers currently working on its recovery. Electronics do sometimes simply fail from age, particularly components that have never once been powered down for maintenance in nearly half a century. Either explanation is consistent with the evidence, Both might even be partially true. Neither can be confirmed, because Voyager 1 is not a spacecraft that can ever be returned to a laboratory bench for inspection. Whatever killed that chip, the code that had lived on it, code the flight data subsystem needed to package data correctly, was permanently gone. That left the team with a very specific engineering puzzle. How do you replace lost software on a piece of hardware you can never physically reach again? The answer they arrived at was to take the code that used to live on the dead chip, break it apart into smaller fragments, and tuck those fragments into whatever small pockets of unused memory remained scattered elsewhere within the flight data subsystem. It is a strategy that sounds almost too simple to work, and it turned out to be considerably harder to execute than it sounds. The routines that had been lost were not incidental. They were instructions the spacecraft relied on constantly, code responsible for packaging science and engineering data into the exact format the transmitter expected before sending it home. Originally, that code had been written to live together in one contiguous block of memory, with different sections calling on each other in a precise, predetermined sequence. The way a small factory assembly line depends on each station being exactly where the next station expects it to be, breaking that code into separate fragments and scattering them across. Whatever tiny gaps remained meant the team also had to rewrite every single reference elsewhere in the system that pointed to the code's original location, updating every internal call so it correctly pointed to wherever its target routine now actually lived. A single incorrect pointer, one address left unchanged, and the flight data subsystem would attempt to execute a routine that no longer existed in that location, sending the spacecraft back into meaningless repetition, or worse, causing the system to lock up entirely with no way to intervene remotely. The very first obstacle the team ran into was simply finding enough free space. There was no single unused region large enough to hold the relocated code as one unbroken piece. 46 years of continuous operation meant that essentially every byte of Voyager 1's onboard storage had long since been allocated to some function or another. To make room for the patch, the team had to find something to delete. Some piece of code doing no useful work anymore that could be safely erased to free up space elsewhere. They found some of that unused code in an unexpectedly poignant place. Tucked inside the flight data subsystem's memory were instructions written back in the 1970s, specifically to manage Voyager 1's flyby of Jupiter, an encounter that had taken place in March of 1979 and had never needed to happen again. That code had been sitting untouched in memory for 45 years, a leftover instruction set for a single planetary encounter that was already ancient history by any measure. It was deleted to make room for the new patch, a piece of software originally written to guide a spacecraft past the largest planet in the solar system, ultimately surviving long enough only to be erased, so that the same spacecraft could survive a memory failure in interstellar space decades later. The first working patch was transmitted on the 18th of April, 2024. Carrying relocated code responsible for packaging the spacecraft's engineering telemetry, the data describing temperatures, power levels, and the general health of Voyager 1's systems. Nobody on the team had been able to reliably answer basic questions about the spacecraft's condition for 5 months at that point. Was the temperature within safe ranges? Were the instruments drawing the power the team expected? The patch traveled outward at the speed of light, arriving at the spacecraft nearly a full day later. Voyager 1 received it, processed it, and began transmitting again. On the 20th of April, the response reached Earth. The engineering data stream was clean, readable, and made sense for the first time since the previous November. Temperatures were normal, power levels were holding steady, the instruments were sitting idle, waiting for further instructions Fixing the science data took longer because each individual instrument, the plasma wave subsystem, the magnetometer, the cosmic rays subsystem, and the low-energy charged particle instrument, needed its own relocated fragment of packaging code, its own carefully updated set of pointers. The team worked through them methodically across May and into June of 2024. On the 13th of June, the last of the spacecrafts for active science instruments came back online and began returning usable data. In total, 5 months of effectively useless transmissions, resolved by identifying a single failed chip, fragmenting decades-old code into pieces, recalculating every pointer that referenced it, and transmitting the fix across roughly 24 billion kilometers to a computer built before most of the engineers who repaired it were even born. It is worth pausing on something that becomes obvious once you look at the discovery and the breakdown side by side. Both events ran through the exact same hardware, the faint, persistent hum that Stella Ocker pulled out of the archived plasma wave data, and the broken telemetry stream that took the Jet Propulsion Laboratory 5 months to repair, were both processed by the same antennas, the same wiring, and the same flight data subsystem. The instrument quietly revealing the fine structure of interstellar space for years, and the component whose failure nearly ended the mission's ability to communicate at all, were one and the same machine. The discovery and the near-catastrophic failure did not happen to 2 different spacecraft or 2 different eras of the mission. They happened inside the same aging hardware, only a few years apart. That connection matters because it points toward the deeper problem the Voyager team is actually managing, which has nothing to do with any single chip and everything to do with the fact that the entire spacecraft is slowly, steadily running out of everything it needs to keep functioning. Understanding why requires a short detour into how Voyager 1 generates electricity in the first place, because it is not doing anything as familiar as solar power. Solar panels are useless this far from the Sun. At Jupiter's distance, sunlight is already about 25 times weaker than at Earth. At Voyager 1's current distance, it is thinner still, far too faint to generate meaningful power. Instead, Voyager 1 runs on a radioisotope thermoelectric generator, a device that produces electricity not from sunlight but from heat, specifically the heat released by the natural radioactive decay of a specific isotope, plutonium-238. As that isotope decays, it releases energy in the form of heat, and a set of thermocouples inside the generator converts a portion of that heat directly into electrical current. No moving parts required, a technology originally developed for exactly this purpose, providing steady, reliable power for missions traveling too far from the Sun for solar panels to work. For durations measured in decades rather than years, plutonium-238 has a half-life of about 88 years, meaning that roughly every 88 years, half of the original radioactive material will have decayed into other elements, steadily producing slightly less heat, and therefore slightly less electricity, with every year that passes. The decline is gradual and highly predictable, but it never stops and it never reverses. Voyager 1 loses roughly 4 watts of generating capacity every single year. That number sounds modest on its own, but multiplied across nearly 5 decades of continuous operation, the spacecraft now has less than half of the electrical power it launched with in 1977, and the trend continues without pause. This is the fundamental constraint underlying every difficult decision the Voyager team has had to make in recent years. There is no way to add power back to the system. There is no way to slow the decay of the plutonium. The only lever available to engineers at the Jet Propulsion Laboratory is deciding which systems get to keep drawing from an ever-shrinking budget, and which systems have to be permanently switched off to keep the spacecraft's most essential functions, communication chief among them, alive for as long as possible. The consequences of that shrinking budget have become concrete and specific in just the past couple of years. The cosmic ray subsystem, the very instrument that helped confirm Voyager 1's crossing of the heliopause back in 2012, was permanently shut down on the 25th of February, 2025, not because it had malfunctioned, but because the power it required was needed elsewhere. The low-energy charged particle instrument, which had been measuring ions and electrons in the surrounding interstellar medium continuously since launch, followed on the 17th of April, 2026. Neither shutdown reflected a preference on the part of the team. Both were forced choices, made because the alternative was risking the loss of the entire spacecraft to an automatic safety shutdown, triggered by insufficient power. One particular incident illustrates exactly how thin those margins have become. On the 27th of February, 2025, a routine roll maneuver, the kind of small orientation adjustment the spacecraft performs regularly to keep its antenna correctly aimed at Earth, caused the available power level to dip further than expected. The dip was enough to raise a genuine concern that an automatic safety system might trigger a broader shutdown to protect the spacecraft. To prevent that outcome, the team made the decision to permanently sacrifice the next instrument scheduled for retirement ahead of plan, which is how the low-energy charged particle instrument's remaining time became numbered. It survived a little over a year longer before finally going dark in April of 2026, exactly as engineers had projected it eventually would. Power was not the only system running out of margin around the same period. The small thrusters responsible for keeping Voyager 1 correctly oriented, firing tiny, precisely timed bursts to nudge the spacecraft's antenna back onto target whenever it drifts, had been slowly clogging for years. Residue left behind by the spacecraft's aging fuel system was gradually narrowing the tiny passages that feed propellant to the thrusters, a completely predictable consequence of running any propulsion system for far longer than it was ever designed to operate. The backup roll thrusters, which had already taken over responsibility for this task back in 2004 after an earlier set of thrusters showed the same kind of degradation, were themselves now on a trajectory toward complete failure, faced with the loss of the only thrusters currently keeping Voyager 1 correctly pointed at Earth. The team's remaining option was to attempt to reactivate the spacecraft's original primary roll thrusters, hardware that had been considered permanently retired for 21 years. The heaters that kept those original thrusters warm enough to function safely had been switched off for 2 full decades, and there was a real, acknowledged risk that attempting to fire cold thrusters after that long a dormancy could cause a catastrophic malfunction rather than a successful reactivation. In March of 2025, engineers at the Jet Propulsion Laboratory ran the test anyway, because the alternative, doing nothing, guaranteed eventual failure regardless. The thrusters fired correctly. The mission's propulsion lead, Todd Barber, later described the outcome as something close to a miraculous recovery. Hardware built in the 1970s successfully restarted after 21 years of complete inactivity, working exactly as needed on the very first attempt, with no opportunity for a second try if it had failed. There is a strange kind of arithmetic sitting underneath this entire story, one worth stating plainly. Voyager 1 is currently transmitting information about the interstellar medium with more clarity and continuity than at any previous point in the history of space exploration, precisely at the moment when the spacecraft producing that information is running out of power, running out of propellant pressure, running out of working memory, and running out of time in every sense an engineer would recognize. The same signal that revealed the fine texture of the space between stars is arriving daily, carried home by a machine whose voice has had to be diagnosed, patched, rerouted, and rescued more times in the past several years than in the 4 decades that preceded them. Sometime in November of 2026, Voyager 1 is projected to reach a genuinely unprecedented milestone, becoming the first object ever built by any species on this planet to sit a full light day away from Earth, a distance of roughly 25.9 billion kilometers. A radio signal transmitted from the spacecraft at that distance will spend an entire 24-hour day simply traveling before it reaches a receiving dish on Earth, and any commands sent in response will spend another full day traveling back out to meet it, for a total of 48 hours between a question being asked and an answer arriving. 2 complete sunrises will pass over the Jet Propulsion Laboratory's control room in Pasadena between the moment an engineer sends a command and the moment any response comes back. No human-made object has ever operated at that kind of distance before, and no mission plan was ever written with the expectation of managing operations across a communication delay that long. By that point, the spacecraft is expected to be running on perhaps 2 of its science instruments, possibly only 1, depending entirely on how the shrinking power budget continues to play out. Current projections from the Jet Propulsion Laboratory suggest that at least 1 instrument should remain operational into the 2030s, though exactly which instrument and for precisely how long depends on variables the team genuinely cannot predict with confidence. How the residue inside the thruster lines continues to behave, exactly how the plutonium's decay curve unfolds in practice versus in theory, and whether some other component somewhere in the spacecraft fails unexpectedly the way the flight data subsystems chip did in 2023. Engineers at the Jet Propulsion Laboratory have already sketched out a further plan, informally nicknamed the Big Bang internally, involving switching off entire groups of heaters simultaneously and replacing some of their function with lower power alternatives in a single coordinated operation. An effort intended to buy the mission another year or 2 of continued function. Beyond that point, the calculations become considerably less certain, and the spacecraft moves into a regime of operation that no mission in the history of spaceflight has ever had to plan for eventually. And there is no way around this. The last functioning instrument will go silent. Even after that happens, the spacecraft's carrier signal, a steady transmitter tone with no data encoded underneath it, is expected to continue for some additional time, faintly detectable by Earth's largest and most sensitive radio dishes for as long as Voyager 1 continues to point correctly and continues to have enough power to keep the transmitter itself running. Eventually, though, the antenna's aim will drift beyond correction, or the available power will drop below whatever minimum the transmitter needs to function, or some final critical component will fail in a way engineers on Earth simply cannot diagnose or repair from this distance. The signal will weaken gradually and then drop below the noise floor of every receiving dish on the planet, and Voyager 1 will continue on, unchanged in its trajectory and speed, moving through the same interstellar medium it has been quietly recording for well over a decade. The persistent hum that Stella Ocker identified in that archived data, the faint, steady signal sitting beneath the noise, the gentle, continuous rain of the interstellar plasma that Cordes described. None of it depends in any way on Voyager 1 remaining alive to hear it. That signal is a property of the interstellar medium itself, not of the spacecraft listening to it. The medium has been producing that faint emission for a length of time measured in the same scale as the galaxy's own history. Long before 1977 and long before any spacecraft existed to record it, it will continue producing that signal long after Voyager 1 eventually falls silent. The only thing that actually changes when the spacecraft's final transmission fades below the noise floor is whether there is still anything close enough out there in interstellar space for anyone on Earth to use as a listening post. It helps, at this point, to widen the frame a little and place Voyager 1 within the small handful of spacecraft that have ever attempted anything like this journey, because the mission did not happen in isolation, and the broader context makes clear just how unusual its continued survival really is. Voyager 1 was not even the first spacecraft aimed at the outer solar system. Pioneer 10 and Pioneer 11, launched in 1972 and 1973 respectively, preceded both Voyagers by several years, flying past Jupiter and, in Pioneer 11's case, Saturn as well, and proving for the first time that a spacecraft could survive passage through the intense radiation belts surrounding Jupiter, information the Voyager team relied on directly when designing their own mission a few years later. Both Pioneer spacecraft eventually fell silent, Pioneer 10's last confirmed signal arriving in January of 2003, and Pioneer 11's in November of 1995, their radioisotope generators having decayed past the point of providing enough power to maintain a detectable transmission. Neither Pioneer spacecraft carried an instrument comparable to Voyager's plasma wave subsystem, and neither survived long enough to reach interstellar space in any confirmed sense, though both are still traveling outward, silent, in roughly the direction they were launched. Voyager 2, launched about 2 weeks before Voyager 1, but sent on a slower trajectory that allowed it to also visit Uranus and Neptune, remains the only other spacecraft to have crossed into interstellar space, doing so in November of 2018 along a completely different heading from its twin. Because Voyager 2 took a different path, it crossed the heliopause at a different location and distance from the Sun than Voyager 1 did, giving researchers to independent data points describing the boundary's shape, useful because the heliopause is not a perfect sphere. It bulges and compresses depending on local solar wind pressure and the surrounding interstellar pressure, closer to the shape of a windsock than a ball, and having to spacecraft sample it from different angles has been essential to mapping that shape at all. Voyager 2 also happens to still be operating its plasma science instrument, a device that directly measures the density, temperature, and speed of surrounding particles, rather than listening passively the way Voyager 1's plasma wave subsystem does, giving scientists complementary techniques for studying the same general environment from two different locations in the sky. Beyond the two Voyagers, only one other spacecraft is on a trajectory that will eventually carry it out of the solar system entirely. New Horizons, launched in 2006, famous for its close flyby of Pluto in 2015 and its more distant encounter with a small Kuiper belt object called Arakoth in 2019. New Horizons carries far more modern electronics than either Voyager, an advantage of nearly 3 decades of progress in miniaturization and radiation-hardened chip design, but it also carries a much smaller radioisotope generator, meaning it faces its own version of the same shrinking power budget problem on a somewhat different timeline. It will likely take New Horizons several more decades to reach the distances Voyager 1 has already traveled. Both Voyager spacecraft also carry something unrelated to their scientific instruments entirely: a phonograph record made of gold-plated copper, containing greetings in dozens of languages, a selection of music spanning multiple cultures and centuries, and encoded images depicting life on Earth, assembled under the direction of a committee, led by astronomer Carl Sagan specifically, for the remote possibility that some other intelligent species might one day recover the spacecraft long after its instruments have gone silent and its human builders are gone. That record was never expected to be read by anyone anytime soon. The nearest star system lies years away, even at the speed of light, and Voyager 1 is moving so much slower than that reaching the vicinity of another star system, let alone being intercepted by anyone capable of playing the record, would require a span of time measured in the tens of thousands of years at minimum. The record was always a message with an almost incomprehensibly long delivery window, a strange companion piece to a set of scientific instruments that, by contrast, have already delivered results decades ahead of anyone's expectations, none of Voyager 1's continued communication with Earth would be possible without the ground infrastructure built specifically to catch impossibly faint signals from deep space. And that infrastructure deserves some attention of its own, because the engineering challenge is nearly as remarkable as anything happening aboard the spacecraft itself. The Deep Space Network consists of 3 groups of large radio antennas positioned roughly 120 degrees apart around the globe, in California, in Spain, and in Australia, spaced deliberately so that as Earth rotates, at least one station always has a clear line of sight to any given spacecraft operating beyond Earth's orbit, regardless of the time of day. Voyager 1's signal is currently received primarily by the Deep Space Network's complex near Canberra, Australia, using dishes up to 70 meters across, structures large enough to be visible from the air, engineered specifically to collect and focus radio waves that arrive at power levels almost too small to describe in intuitive terms. By the time a signal transmitted from Voyager 1's 23-watt transmitter, a power level lower than a typical refrigerator light bulb, has traveled 24 billion kilometers. It is spread out across an area so enormous that only an almost vanishingly small fraction of the original energy actually strikes the receiving dish on Earth. This spreading follows a basic and unavoidable rule of physics called the inverse square law. A signal radiating outward in all directions loses intensity in proportion to the square of the distance traveled, meaning double the distance reduces the received power to 1/4. And Voyager 1's distance has increased by an enormous factor since launch. By the time it reaches Earth, the signal carries less power than a fraction of a billionth of a watt. A signal so weak that, by some estimates, the total energy collected from Voyager 1 across the spacecraft's entire multi-decade transmission history would not be enough to power a single household light bulb for even a fraction of a second. Extracting anything meaningful from a signal that faint requires extraordinarily sensitive receivers, careful filtering to separate the signal from background radio noise, generated by everything from Earth's own atmosphere to distant galaxies, and enormous dishes simply to gather enough of that vanishingly thin trickle of energy to work with at all. There is a useful concept from information theory that captures exactly what has been shrinking throughout this entire story, something engineers call channel capacity, a formal measure developed by mathematician Claude Shannon in the middle of the 20th century, of the maximum rate at which information can reliably travel through any communication channel, given its available power and the level of background noise it has to compete against. Every parameter that determines Voyager 1's channel capacity has been degrading simultaneously for decades. The spacecraft's transmitter weakens slightly as its own power supply shrinks. The signal spreads across an ever-increasing distance according to the inverse square law described above. The background noise floor of the universe itself, meanwhile, stays essentially constant because it is set by fundamental physics rather than anything happening aboard the spacecraft. The result is a communication channel whose maximum usable capacity has been shrinking steadily since the moment of launch, and will continue shrinking until, eventually, it reaches zero. Every bit of data that has ever come back from Voyager 1, from routine engineering telemetry to Stella Ocker's carefully extracted plasma hum, was squeezed through a channel already operating close to its fundamental limit. And that limit keeps tightening every year. It is worth spending a little more time on why continuous measurements of interstellar plasma density actually matter to astrophysics. More broadly, beyond simple curiosity about what lies just outside our solar system, because the answer connects directly to some of the biggest open questions. In the study of our galaxy's structure, the Sun sits inside a relatively small, diffuse cloud of partially ionized gas that astronomers call the local bubble, a region roughly a few hundred light-years across, thought to have been carved out by the combined effects of supernova explosions from massive stars that lived and died in this part of the galaxy tens of millions of years ago. Voyager 1 and Voyager 2 are still, in a cosmic sense, extremely close to home, sitting right at the inner edge of this local structure, but they represent the only direct, in-place measurements humanity has ever obtained of the material actually filling that structure. Every other piece of information astronomers have about the interstellar medium anywhere else in the galaxy comes indirectly, inferred from how starlight is absorbed or scattered as it passes through intervening gas and dust, or from radio observations of hydrogen clouds, or from the way cosmic rays scatter and lose energy as they travel toward Earth. Voyager's readings are the only ground truth measurements available, a single, precious data point against which every indirect method used to study interstellar gas elsewhere in the galaxy can be calibrated and checked. That calibration matters because the interstellar medium plays a direct role in one of the more persistent puzzles in astrophysics, the behavior of cosmic rays, high-energy particles that stream through the galaxy and occasionally strike Earth's atmosphere, generating cascades of secondary particles that reach the ground. Cosmic rays are deflected and scattered by magnetic fields and by the density structure of the plasma they pass through on their way toward us, meaning that understanding the fine-grained texture of that plasma, the exact kind of small-scale turbulence and density fluctuation that Ocker's persistent hum allowed scientists to finally measure directly, feeds directly into models describing how cosmic rays propagate across the galaxy and eventually reach our detectors. Get the local interstellar medium's structure wrong, and every downstream calculation about cosmic ray behavior inherits that error. There is a similar connection to the study of the heliosphere's overall shape and behavior, an active area of heliophysics research pursued using instruments like the Interstellar Boundary Explorer, a NASA satellite launched in 2008 specifically to map the heliosphere's outer boundary from Earth orbit, using a technique that detects neutral atoms produced when the solar wind collides with interstellar gas at the boundary and bounces some particles back inward. That satellite's global maps, combined with Voyager's direct, in-place readings from two very specific points along the boundary, together provide a far more complete picture of the heliosphere's true shape than either technique could offer alone. The heliosphere protects the solar system to a meaningful degree from a portion of the cosmic ray flux and interstellar material that would otherwise reach the inner planets more directly, and understanding exactly how that protective bubble is shaped, how it responds to changes in solar activity over an 11-year solar cycle, and how it has likely changed shape and size over much longer timescales as the Sun's position within the galaxy has shifted, all depends on exactly the kind of continuous, fine-grained plasma measurements that Voyager 1's aging plasma wave subsystem happens to be uniquely positioned to provide. The pattern of missing a real signal simply because nobody had built an instrument sensitive enough, or nobody had thought to look in exactly the right place. extends into two more fields worth mentioning specifically, because both connect directly back to the theme running underneath this entire story: the cosmic microwave background. The faint afterglow of radiation left over from roughly the first few 100,000 years after the Big Bang is one of the most famous examples of an accidental discovery hiding in what looked like background noise. In 1964, two researchers at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were working with a highly sensitive radio antenna originally built for satellite communication, and kept detecting a faint, uniform hiss of microwave radiation coming from every direction in the sky. Regardless of where they pointed the instrument, their first assumption was that something was wrong with their equipment. They cleaned pigeon droppings out of the antenna, checked every wire, and the signal remained. It took a conversation with theoretical physicists working at nearby Princeton University, who had independently predicted that exactly this kind of leftover radiation should exist if the Big Bang theory was correct, to realize that what Penzias and Wilson were seeing as an annoying, uniform hiss was actually direct observational evidence of the universe's earliest moments. Faint radiation that had been washing over Earth constantly, completely undetected, until an instrument sensitive enough and a team paying close enough attention finally noticed it. The search for dark matter follows a similar arc, though the ending has not yet been written. Multiple independent lines of astronomical evidence, from the rotation speeds of galaxies to the way galaxy clusters bend light through gravitational lensing to the detailed structure of the cosmic microwave background itself, all point toward the existence of a form of matter that does not emit, absorb, or reflect light, making up roughly 5 times more of the universe's total matter content than all the ordinary atoms that make up stars, planets, and everything visible combined. Despite decades of increasingly sensitive experiments, many of them built deep underground in old mines, specifically to shield delicate detectors from cosmic ray interference, no laboratory on Earth has yet directly detected a single dark matter particle interacting with ordinary matter. That absence of a detection does not mean dark matter is not there. The astronomical evidence for its gravitational effects is overwhelming and comes from far too many independent methods to dismiss. It means the interaction, if it exists at all in a form current detectors could catch, is weaker than the current generation of instruments can measure. Precisely the same situation. The interstellar medium's persistent hum was in for the first 5 years after Voyager 1 crossed the heliopause, before Stella Ocker finally noticed it, sitting quietly beneath the noise floor. A closely related search for deliberate radio signals from another technological civilization, sometimes called technosignatures, has run for more than 6 decades using this same underlying logic, listening across enormous stretches of the radio spectrum for anything that looks artificial rather than natural. Modern efforts, like the privately funded Breakthrough Listen initiative, launched in 2015, use some of the largest radio telescopes on Earth to scan millions of star systems across a vast range of frequencies. And so far, the result has been silence. As with dark matter, that silence proves very little on its own. It could mean nobody nearby is transmitting in a way current instruments would recognize. It could mean the search has not yet covered enough of the sky, or enough of the radio spectrum, or run for long enough. It is, in the truest sense, exactly the same open question chords and the Voyager team were sitting with before Ocker went looking. Is the silence real? Or is it simply quieter than anyone has managed to listen for yet? There is an additional layer to this repair story worth drawing out, because it says something interesting about engineering knowledge itself, not just about hardware. Successfully diagnosing and patching a 46-year-old computer required more than just clever fragmenting and pointer math. It required access to documentation written in the 1970s, describing a system built using design conventions and programming, approaches that have almost entirely disappeared from modern practice. Voyager's onboard software was written directly in assembly language, a low-level form of programming that gives extremely precise control over exactly what a processor does with every instruction, but which requires the programmer to manage memory addresses, variable locations, and processing steps manually. None of the automated safety nets or higher-level abstractions that make modern software development faster and less error-prone. Modern spacecraft software is typically written using higher-level languages that automatically handle much of that bookkeeping, trading some of Voyager's fine-grained efficiency for considerably more maintainable and less error-prone code, an appropriate trade-off for missions that are not also being asked to survive nearly 5 decades of continuous, unattended operation on hardware nobody can ever touch again. Part of what made the 2024 repair possible at all was the fact that a handful of engineers still actively working on the Voyager mission had either worked on the spacecraft's original design decades earlier or had spent years afterwards studying its documentation closely enough to understand the system as thoroughly as its original 1970s designers had. That kind of institutional knowledge is not easily replaced. Much of it exists only in printed documents from an earlier era of engineering, and in the memories of a small, aging group of specialists. A genuine and openly acknowledged concern within NASA and the Jet Propulsion Laboratory as the mission continues, since every year that passes increases the risk that a critical piece of undocumented knowledge about the spacecraft's original design might simply not be available the next time something goes wrong. In some sense, keeping Voyager 1 talking has become as much a challenge of preserving decades-old engineering knowledge as it is a challenge of managing the spacecraft's physical hardware. This tension between an aging, simple, and remarkably robust design on one hand, and a shrinking pool of people who deeply understand that design on the other, is part of why NASA has occasionally discussed what a genuine successor mission might look like. One built from the outset with the explicit goal of reaching interstellar space and continuing to operate for decades afterward, rather than achieving that milestone as an unplanned bonus outcome of a mission designed for something else entirely. Proposals for a dedicated interstellar probe carrying modern, radiation-hardened instruments specifically designed to study the heliopause boundary and the interstellar medium beyond it have circulated within the scientific community for years, though none has yet received the funding or formal mission approval needed to move forward. Any such mission, even launched with a substantially faster propulsion system than either Voyager ever carried, would likely still take a decade or more simply to reach the boundary Voyager 1 crossed in 2012, underscoring just how valuable it is that Voyager 1's aging instruments remain functional at all, gathering data no other spacecraft is currently positioned to collect, and none will be positioned to collect again for a very long time. It is also worth noting how much smaller the team behind Voyager 1 has become compared to the effort that once supported it. During the Jupiter and Saturn flybys in the late 1970s and early 1980s, mission control rooms were staffed with hundreds of engineers and scientists working around the clock, coordinating a rapid sequence of planetary encounters that offered no opportunity for a repeat attempt if anything went wrong. Today, decades later, a much smaller team, many of them responsible for supporting several other missions simultaneously, keeps both Voyager spacecraft operating on a fraction of the staffing and a fraction of the budget the mission once commanded. Suzanne Dodd, who has served as the Voyager project manager at the Jet Propulsion Laboratory, has spoken publicly about how much institutional knowledge the current team has had to reconstruct essentially from scratch. working from decades-old documentation to understand systems that few people alive still remember designing firsthand. Keeping a nearly 50-year-old spacecraft functioning at this distance is not simply a matter of good engineering. It also depends on a small number of dedicated specialists choosing, year after year, to keep showing up for a mission that receives a tiny fraction of the funding and public attention of NASA's larger, more recent projects. If you have found this kind of story interesting, following along for future updates costs nothing and helps more of this material reach people who would enjoy it just as much. So, subscribing or hitting the notification option, if the platform you are watching this on offers one, is a straightforward way to make sure you do not miss whatever the Voyager team, or the broader search for signals hiding beneath the noise floor, turns up next. There remains a considerable amount that nobody currently understands with certainty about Voyager 1's remaining years. The exact cause of the flight data subsystem chip failure in 2023, whether it was a single cosmic ray strike or simple age-related degradation, will most likely never be confirmed one way or the other, since there is no way to physically examine the failed component. How the residue inside the thruster fuel lines will continue to behave over the coming years, and whether the reactivated primary thrusters will continue functioning reliably after 2 decades of dormancy, remains an open and closely monitored question rather than a settled one. Exactly how long the plutonium-powered generator will continue to support even a single functioning science instrument depends on a combination of predictable radioactive decay and considerably less predictable behavior from aging electronics and mechanical components that have never operated under quite these conditions before on any spacecraft. For this long, there is also an open scientific question embedded directly in the story of Ocker's discovery that nobody has fully answered yet. Whether the persistent hum detected in the interstellar plasma changes in character or strength as Voyager 1 continues moving further from the heat deeper into the surrounding medium, and whether that change, if it exists, might reveal something about the boundary between the local bubble the sun sits inside and whatever lies beyond its edges. Answering that question requires exactly the kind of continuous, patient monitoring that has defined this entire story, using an instrument that may or may not still be operating by the time enough additional data has accumulated to say anything definitive. Voyager's measurements do not exist in isolation. Over the past several years, NASA has also operated the Parker Solar Probe, launched in 2018, on a very different kind of mission. Rather than traveling as far from the sun as possible, Parker repeatedly dives closer to the sun than any spacecraft in history, directly sampling the solar wind at the very source from which it originates, before it has had a chance to spread out, cool, and interact with the wider solar system, where Voyager 1 measures what the solar wind and the surrounding interstellar medium look like after traveling 24 billion kilometers and crossing entirely into a different physical regime. Parker measures the same general phenomenon at the opposite extreme, within a few million kilometers of the sun's visible surface. Together, these two missions, operating at wildly different distances and studying complementary parts of the same overall system, give researchers a far more complete picture of how the solar wind evolves across its entire journey than either mission could provide on its own. From its violent origin near the sun's corona to its final, faint interaction with the interstellar medium at the edge of the heliosphere, the timing of that broader research effort matters, because the sun's activity is not constant. It follows an approximately 11-year cycle, alternating between periods of heightened activity, called solar maximum, marked by frequent sunspots, flares, and coronal mass ejections, and quieter periods called solar minimum. The sun reached a solar maximum around 2024, and the resulting increase in coronal mass ejections has meant more frequent shockwaves, traveling outward through the solar system, some of which will eventually reach Voyager 1's location and register on its plasma wave instrument as one of Quartz's lightning flashes, offering researchers fresh opportunities to compare shock-driven measurements against the steady, persistent hum Ocker identified, refining the relationship between the two kinds of signal a little further with every event that arrives. Zooming out from all of these individual details, what makes Voyager 1's story genuinely unusual, rather than simply another entry in the long list of aging engineering marvels, is the specific combination of two things happening at once inside the same machine. A scientific discovery that depended entirely on someone finally listening carefully enough to notice, a signal that had been there the whole time, and a near-catastrophic hardware failure that depended entirely on a team's willingness to diagnose and repair. A computer they could never see, touch, or restart, using nothing but patience, decades-old documentation, and a communication delay measured in days rather than seconds. Both stories are, in their own way, about paying close attention to something faint, whether that faintness comes from a weak plasma oscillation sitting beneath, a noise flaw, or a nearly imperceptible pattern buried inside a corrupted data stream. Both required someone to look carefully at what everyone else might reasonably have dismissed as nothing. Right now, tonight, a spacecraft older than most of the people who will ever watch a video describing it continues, transmitting from roughly 24 billion kilometers away, still pointed at a small blue planet it can no longer see with any of its remaining instruments, its remaining hardware still recording the fine texture of the space it moves through, one faint signal at a time. Every reading that arrives at the Deep Space Network's dishes in Canberra represents a small, specific kind of borrowed time, a transmission from a machine that, by almost any reasonable engineering standard applied to its original design, should have gone silent decades ago. The persistent hum that Stella Ocker pulled out of an archive nobody else had thought to search carefully is still arriving. The question of exactly how much longer it will keep arriving remains genuinely open, dependent on plutonium decay curves, fuel line residue, and a small aging team's continued ability to diagnose problems across a communication gap that grows by roughly a light day's distance every few years. It is worth explaining, in slightly more technical terms, exactly why the persistent signal Ocker found carries useful information about plasma density at all, because the underlying physics is elegant and it explains precisely why this particular measurement technique works as well as it does. Charged particles in a plasma, when disturbed, do not simply drift apart randomly. They oscillate collectively, because any local imbalance of positive and negative charge creates an electric field that pulls the particles back toward equilibrium, causing them to overshoot, reverse, and oscillate back and forth at a characteristic frequency that depends directly on how many charged particles are packed into a given volume. Denser plasma oscillates at a higher characteristic frequency. Thinner plasma oscillates more slowly. This relationship, sometimes called the plasma frequency, means that simply measuring the frequency at which the surrounding plasma is oscillating, exactly what Voyager 1's antennas passively pick up, gives researchers a direct, quantitative measurement of the local electron density without needing to catch a dramatic shock event at all. That is precisely why Ocker's discovery of a persistent, narrow-frequency signal mattered so much. It meant the electron density of the interstellar medium immediately surrounding Voyager 1 could be calculated continuously, day after day, rather than only during the rare, brief windows when a solar shock happened to pass through and disturb the plasma violently enough to produce an obvious, easily identified signal. That density measurement, in turn, connects to a decades-old open question in heliophysics: exactly how the interstellar medium's density changes as you move outward from the heliopause, and whether that density profile matches theoretical models built before Voyager 1 ever provided direct, in-place confirmation. Prior to Ocker's persistent signal, those models rested almost entirely on indirect evidence and a handful of isolated shock measurements, each one a brief snapshot separated by months or years of uncertainty. With a continuous measurement technique available, researchers were finally able to track how density varies with position in far more detail, confirming some aspects of the existing theoretical picture while revealing unexpected small-scale structure. The turbulence and local density fluctuations mentioned earlier, that no existing model had specifically predicted in that much detail. Science, in this particular case, moved forward not because of a dramatic new instrument or an expensive new mission, but because someone finally paid enough attention to data that had already been sitting in an archive for years, waiting to be properly examined. The infrastructure making any of this possible traces back much further than Voyager itself. The Deep Space Network was established in 1958, originally to track and communicate with the earliest American satellites, and shortly afterward, the first robotic missions sent toward the Moon and nearby planets. Its capabilities have been continuously upgraded across nearly 7 decades of operation. Larger dishes, more sensitive receivers, more sophisticated signal processing. Precisely because every new generation of spacecraft has pushed communication requirements further than the previous generation's ground infrastructure could handle, Voyager 1, in a very real sense, has spent the past several decades acting as a continuous stress test for exactly how far that infrastructure could be pushed, forcing incremental improvements in deep space communication technology that have gone on to benefit essentially every mission NASA has launched since. From Mars rovers to outer planet orbiters to the New Horizons mission that eventually followed Voyager's example out toward the edge of the solar system and beyond. It is easy to lose track of just how much time is actually being discussed here, so it helps to anchor the numbers in something more familiar. Voyager 1 launched in September of 1977, the same year the first Star Wars film reached theaters and roughly a year before the first commercial cell phone network began development anywhere in the world. The spacecraft carries computer hardware with a combined processing capability far below that of a modern digital wristwatch, let alone a smartphone, and it has been operating continuously, without a single hardware reboot of the kind any modern computer receives regularly, for very close to 50 years. Most of the engineers who originally built Voyager 1's systems have long since retired, and a meaningful number have passed away, meaning the spacecraft has genuinely outlived a portion of its own design team, still transmitting data back to a control room staffed by engineers who, in some cases, were not yet born when the mission launched. In February of 1990, at the request of astronomer Carl Sagan, the Voyager team turned the spacecraft's camera around and captured a final series of images looking back toward the inner solar system, before the cameras were permanently switched off to conserve power for other systems. In one of those frames, taken from a distance of roughly 6 billion kilometers, Earth appears as a single point of light less than a pixel across, a tiny, pale speck suspended in a band of scattered sunlight, a single dot among the frame's grain and glare. That image, often referred to informally as the pale blue dot photograph, remains, even decades later, one of only a small number of images ever taken of Earth from beyond the orbit of Neptune, and it was captured using a camera system that has not operated since. having been deliberately shut down not long afterward, specifically because Voyager 1 needed every remaining watt of power for the instruments, still capable of returning genuinely new scientific information. A decision that, in retrospect, previewed by more than 3 decades, the exact kind of trade-off the mission's engineers are still making today. Deciding which systems earn the right to keep drawing from an electrical budget that only ever shrinks. Single event upsets, the radiation-induced glitches that remain one of the 2 leading explanations for what actually killed the memory chip inside. Voyager 1's flight data subsystem are not unique to this mission. They have affected numerous spacecraft over the decades, sometimes with far more dramatic consequences. The Galileo spacecraft, which studied Jupiter and its moons throughout the 1990s, experienced repeated computer resets attributed at least partly to the intense radiation environment surrounding Jupiter, a much harsher environment than anything Voyager encountered during its brief flyby decades earlier. Even spacecraft operating much closer to home, in Earth orbit, regularly experience single-event upsets while passing through regions of intensified radiation such as the South Atlantic anomaly, a region where Earth's protective magnetic field dips unusually close to the surface, allowing more energetic particles to reach satellite altitudes than elsewhere along the same orbit. Modern spacecraft designers account for this risk directly, using radiation-hardened processors, error-correcting memory that can automatically detect and repair certain kinds of single-bit corruption without any ground intervention at all, and redundant systems specifically designed so that a single upset in one component does not cascade into a broader failure the way it very nearly did aboard Voyager 1 in 2023. Voyager's hardware, again, predates essentially all of these modern radiation hardening techniques, which is precisely why a single failed chip was capable of disabling such a critical function in the first place, and precisely why fixing it required such an unusual, manual, almost artisanal software repair rather than an automated correction the spacecraft could have performed on its own. Engineers within NASA have pointed to the 2023 and 2024 Voyager recovery effort as a genuinely valuable case study for the broader discipline of long-duration spacecraft design, not because anyone would deliberately choose to build a future mission with 1970s-era radiation vulnerability, but because the recovery demonstrated just how much flexibility can be preserved in even an extremely old, extremely constrained system, provided that system's original documentation survives. Its logic remains genuinely understandable decades later, and a team remains willing to think creatively about fragmenting and relocating code inside a memory space that offers no room whatsoever for error. Some of those lessons are already informing discussions about how future deep space missions, particularly any eventual dedicated interstellar probe, should be designed with an eye toward remaining serviceable in this remote, software-only sense, for periods measured in decades rather than years. An explicit design goal that simply did not exist when Voyager 1's original engineers were writing assembly code in the early 1970s. It is worth taking one more step back to appreciate just how far Voyager 1's speed actually falls short of what would be needed to reach another star system in any humanly meaningful span of time, because the comparison puts both the mission's genuine achievement and its ultimate limitations into proper perspective. Voyager 1 is currently traveling away from the Sun at roughly 61,000 kilometers per hour, fast enough that, in the time it takes to read this sentence, it has already covered a distance greater than the length of most cities on Earth. That speed, extraordinary by any everyday standard, is nowhere near fast enough to make interstellar travel to another star system practical on any timescale relevant to a human life, or even to many human generations. The nearest star system to our own, Alpha Centauri, lies a little over 4 light-years away, at Voyager 1's current speed, and setting aside the fact that the spacecraft is not actually headed in that direction at all. Covering that distance would take in the range of 80,000 years, a span of time longer than the entire history of human civilization as currently understood, stretching back well before agriculture, before written language, before most of what anyone would recognize as recorded history. That comparison is not meant to diminish what Voyager 1 has accomplished. It is meant to sharpen exactly what the accomplishment actually is. Voyager 1 has not traveled to another star system, and it never will. What it has done, and what makes it genuinely unprecedented, is travel far enough beyond our own solar system's boundary to sample, directly and continuously, an environment that had never before been measured by anything built by human hands. Close enough to home that the round-trip communication delay, while brutal by any ordinary standard, still measures in mere hours rather than centuries. And far enough from home that the environment it is sampling belongs unambiguously to the wider galaxy, rather than to our own solar system. It occupies a genuinely narrow and valuable middle ground, reachable, in a communication sense, and yet definitively beyond the sun's direct influence. A combination no other spacecraft has matched, and none currently in operation is likely to match again for a very long time. Looking ahead, several distinct threads of research and monitoring are likely to continue running in parallel for as long as Voyager 1 keeps transmitting anything useful at all. Researchers at Cornell and elsewhere will keep mining the plasma wave archive for subtler patterns in the persistent hum, watching for any long-term drift in frequency or strength that might reveal how the interstellar medium's density changes as the spacecraft continues its slow journey further from the heliopause. Engineers at the Jet Propulsion Laboratory will keep monitoring the spacecraft's remaining power budget on essentially a monthly basis, refining exactly when the next heater group needs to be switched off and which lower power alternative can absorb its function with the least disruption to whatever instruments remain active at the time. And a small number of specialists will keep working to preserve, document, and where possible, transfer their understanding of Voyager's 1970s-era systems to younger engineers. An ongoing effort explicitly aimed at making sure that the next diagnostic challenge, whatever it turns out to be, does not arrive at a moment when nobody remaining on the team fully understands the hardware well enough to respond. None of these efforts are expected to reverse the fundamental trajectory. Voyager 1's power will continue declining. Its instruments will continue being switched off one at a time, in whatever order the shrinking budget forces. Eventually, sometime probably in the 2030s, based on current projections, though possibly sooner if an unexpected failure intervenes, the last functioning science instrument will fall silent, followed some additional time later by the carrier signal itself. What nobody currently knows with any real precision is the exact date any of that will happen, because the underlying uncertainty, how residual fuel line clogging behaves, how individual chips age under conditions nobody designed them for, whether some other quiet hardware failure is already accumulating somewhere inside a spacecraft that cannot be inspected, means every projection carries a wide margin of error that only narrows as each additional year of continued operation confirms or revises the models engineers are working from. That open uncertainty is, in its own way, exactly what makes the mission worth continuing to pay attention to. Every additional month of continued transmission is not simply extra time on a spacecraft that was always going to keep working regardless. It is additional, unrepeatable data from an environment no other instrument is currently sampling, purchased at the cost of an aging machine's rapidly shrinking margins. and delivered by a team whose expertise in operating that specific machine is itself a genuinely finite and non-extenuable resource. Set the two signals from this story side by side one final time, because that is really what all of it comes down to. The first signal is the persistent, faint, monotone hum that Stella Ocker pulled out of 6 years of archived recordings, a property of the interstellar medium itself, present for far longer than any human instrument has existed to record it, and destined to remain present long after every spacecraft humanity has ever launched has gone permanently silent. It required nothing from Voyager 1 except a functioning antenna and someone on Earth, patient enough to look through data that everyone else had already decided contained nothing worth examining. The second signal is Voyager 1's own voice, the carefully packaged stream of telemetry and science data that very nearly stopped making sense permanently in November of 2023, rescued only through a combination of a cleverly designed diagnostic command, a week of careful decoding, and months of painstaking 45-hour round-trip software surgery performed on a computer nobody will ever touch again. That signal depends entirely on the spacecraft staying alive, on plutonium that keeps decaying whether anyone wants it to or not, on thrusters that were never meant to still be firing after 50 years, and on a team small enough to fit in a single room somewhere at the Jet Propulsion Laboratory, continuing to show up and continuing to remember how a machine built before most of them were born actually works. One of those signals is patient and indifferent, entirely unconcerned with whether anyone is listening. The other is fragile, aging, and remarkable precisely because it has continued speaking for so much longer than anyone building it in the 1970s had any real reason to expect. Both arrived at the same antenna, processed through the same worn hardware, within a few years of each other, and the genuinely interesting part of this story has never really been about Voyager 1 specifically. It is about what it actually costs to keep listening at this distance, how briefly that particular window tends to stay open, and how much can still be discovered simply by paying close attention to the parts of a signal that everyone else assumed were empty. It is easy to forget, looking only at the current state of a spacecraft running on 2 instruments and a shrinking power budget, just how much scientific output the Voyager program has already produced over nearly 5 decades. Between the 2 spacecraft, Voyager 1 and Voyager 2 returned the first close-up images of Jupiter's turbulent atmosphere and its intricate ring system of moons, discovered active volcanic activity on Jupiter's moon, Io, the first confirmed volcanic activity found anywhere in the solar system beyond Earth, and revealed the complex, layered structure of Saturn's rings in detail no ground-based telescope could match. Voyager 2 went on to provide the only close-up images humanity has ever obtained of Uranus and Neptune, encounters that remain, decades later, the sole source of detailed information about either planet's atmosphere, moons, and magnetic field, since no follow-up mission to either world has yet been funded or launched. Discoveries made during those flybys reshaped textbook understanding of the outer solar system and continue to inform every subsequent mission proposal aimed at revisiting either planet, the interstellar phase of the mission. Everything described throughout this account represents an extension nobody involved in the original 1970s planning explicitly anticipated achieving, made possible only because the spacecraft's builders, working with the reliability standards and generous engineering margins typical of that era, happened to build hardware robust enough to keep functioning decades past its formal mission requirements. That combination of accidental longevity and a small, dedicated team's continued willingness to keep squeezing new discoveries out of aging hardware is, in the end, the actual through line, connecting a 1979 flyby of Jupiter to a 2021 paper about a faint hum in the interstellar medium to a 2024 software patch built entirely out of fragmented, relocated 1970s assembly code. The mission was never designed to still be running now. It simply never stopped, one careful decision at a time. For very close to 50 years, somewhere out past the edge of the sun's influence, moving through a medium that has been humming quietly since long before Earth existed. A machine built by people who mostly assumed it would stop working decades ago keeps sending back one more reading, and then another, for as long as the plutonium keeps decaying just slowly enough, and the team on the ground keeps remembering just enough to make one more day of listening possible.